Chapter 12.3 Testing the independence of two variables. You can also use a chi-square distribution test to determine if two categorical variables are independent of one another. This procedure is known as the chi-square test of independence. Two variables are independent of one another if changes in the level of one variable do not affect the levels of the other variables. Consider the following example. Suppose Best Buy would like to know if the age of a customer affects the brand of digital camera he or she purchased. This information will be used to help design a new promotional campaign. To investigate this relationship, Best Buy collected the data shown in Table 12.28. The data show the frequency with which 150 people, categorized by their age group, purchase various camera brands. Recall from Chapter 2 that this type of table is known as a contingency table, and each observation is known as a cell. In this example, we have two categorical variables, camera brand and age group. Table 12.28 tells us that 30 customers aged 18 to 34 purchased Canon camera. Using the chi-square independent test, we can find out if a pattern exists between the age of customer and the camera brand he or she chooses. We will use alpha equal to 0.05 for this test. Step 1. Identify the null and alternative hypothesis. The null hypothesis for this test is that the two categorical variables are independent of one another. In another word, the age of customer has no effect on the camera brand he or she purchased. Consequently, there is no relationship between the two variables. The hypothesis statement is therefore as follows. Null hypothesis. The camera brand and age of customer are independent of one another. Alternative hypothesis. The camera brand and age of customer are not independent of one another. Step 2. Calculate the expected frequencies. Again, the expected frequencies are calculated under the assumption that there is no relationship between the two categories, or the null hypothesis. As equation 12.5 shows, we calculate the expected frequencies, or FE, for each cell in the contingency table by multiplying the row total by the column total. This results in the divided by the total number of observations. For example, to calculate the expected number of customers who purchase a Canon in the 18 to 34 age group, we need to go back to Table 12.28. The table shows that there were 54 customers in the 18-34 age group, and that a total of 60 customers purchased a Canon. Assuming the null hypothesis is true, the expected frequency for this cell is as follows. FE equal to row total times column total divided by total number of observation equal to 18 to 34 total times Canon total divided by 150 equal to 54 times 60 divided by 150 equal to 21.6. The expected frequency calculation for the remaining cell are shown in Table 12.29. Once again, we need to ensure that the expected frequency for each cell is at least 5 in order to proceed with the chi-square test. If needed, we can combine either rows or column like we did in previous example. Unfortunately, this is not necessary for these examples. Step 3. Calculate the chi-square test statistic, or x-square. We'll use equation 12.1 again with the help of table 12.30 to calculate the chi-square test statistic. The expected frequencies are pulled from table 12.29. Step 4. Determine the chi-square critical value, or x-square alpha. The chi-square test of independent has the following degrees of freedom: r-1 times c-1, where r is the number of rows in the contingency table. C is the number of columns in the contingency table. For our best buy example, we have 3 age group, so R is equal to 3. We also have 3 camera brands, so C is equal to 3. This means our chi-square critical value has R-1 times C-1, or 3-1 times 3-1 equal to 4 degrees of freedom. If we go to the alpha equal to 0.05 column in table 12.5, we'll find that x square alpha is equal to 9.488. Step 5. Compare the test statistic x square with the critical value x square alpha. Because x square equal to 12.14 and this is greater than x square alpha equal to 9.488, we reject the null hypothesis according to table 12.6. Step 6. Determine the p-value. P-value is equal in Excel is equal to chi-sq.dist.rt inside parentheses 12.14, 4 is equal to 0.0163 because p-value is equal to 0.0163 and is less than alpha 0.05, we reject the null hypothesis. Step 7. State your conclusion. By rejecting the null hypothesis, we have found support that there is a relationship between the age group of customer and the camera brand they purchase. So, these categorical variables do not appear to be independent of one another. Comparing the observed and expected frequencies in table 1230, it seems that younger customers favor Canon camera. We make this statement based on the fact that table 12.30 shows 30 customers in this cell when we expected only 21.6 had there been no relationship. Recall that 12.1 was the expected frequency we calculated. Using the same logic, older customers appear to be partial to Sony cameras. This information could help Best Buy and the camera manufacturer target different kind of customer with different kind of promotional campaign. We need to exercise caution with stating the conclusion for a chi-square test of independent. Rejecting the null hypothesis does not allow us to state that one variable caused the other variable to change. We have no proof for that kind of statement. In other words, we cannot go so far as to say that the ages of customers cause them to choose different camera brand. The chi-square test of independence simply identified that there was a pattern between the age groups and camera brands chosen. Thank you.